Right. Okay. Hello, everyone. Welcome to Research Connection Speaker Series. You're joining our special series on physics-informed AI, which brings together insights at the intersection of artificial intelligence and physics and is brought to you by the SOS team and the AI Lab. This curated series explores how physics-informed AI is revolutionizing simulations, design processes, and problem solving across industries. And then I'm going to hand it off to Mara to introduce our speaker for today.
Great. Okay, thank you very much. Hi, everyone, and thanks for joining us today for the third talk in our special series on physics-informed AI. As G mentioned, in this series, we're inviting experts to share cutting-edge advancements in the field. And today, I'm thrilled to introduce our speaker, Zhongyi Li. I'm sure many of us are already familiar with Zhongyi's influential work on neural operators. Zhongyi is currently a PhD student at Caltech, where he is supervised by famous Anima Anand Kumar in the Department of Computing and Mathematical Sciences. His research focuses on developing deep learning methods for solving partial differential equations, particularly pioneering neural operator methods that extend neural networks to operator learning. Zhongyi earned his bachelor's degree in computer science and mathematics from Washington University in 2019, where he was advised by Brendan Juba and Sean Tang. And since then, he has completed 3 internships at NVIDIA from 2022 to 2024. And it is needless to say that Zhongyi's research has been supported by major players like Amazon and NVIDIA. And so, Zhongyi, we are very excited to have you with us today. And without further ado, I hand it over to you.
Thank you, Marion, for the introduction. So I'm very happy to talk here. Today, I'm going to talk about neural operators as a general methods for accelerating scientific computing. So for today's talk, I'm roughly going to cover 3 topics. The first is the general settings of neural operators, and then 2 ongoing research directions. One is self-supervised learning when we have to lack of data computing. Another is to do complex geometries, especially for inverse design. Okay, so first, allow me to show 2 examples we can do with the Fourier neural operators. On the left, it is a weather predictions called forecast-net. It does 30-kilometer predictions over the globe. It can do temperature, velocity predictions about the next 6 hours in the mid-range, cover a week to 2 weeks. So this forecast-net is one of the first models that show it is possible to do data-driven weather forecast. And for example, here, it can model the typhoon Matthew in 2016. We know that the Oscar are striking Florida again, but in this case, it's 2016 case. It can accurately predict the typhoon, and it has a lot of impact. Especially, it can help to save people's life and properties. Another example is the carbon storage. In many cases, in plants or oil industries, instead of release all the carbon into the atmosphere, they can instead store them, inject them under the ground. So they will have several wells and put them into the underground reservoir. So this carbon dioxide will not cause global warming into the air. This simulation is a range of 30 years of the migration of carbon. We want to make sure all the carbon will not release and escape back into the air. And so this is the pressure and the segregation simulations. It's a challenging case for 3D multi-grid simulation. And for all this work, we have been collaborating with scientists and experts. They're really the key ingredients behind all the projects. So the key trick is use the right machine learning models and collaborating with the domain experts to deliver the right answer to the right questions. overall, I'm very optimistic for AI-aided, AI-accelerated computings. We're kind of delivering real-world applications such as weather forecasts. It can also be used in the automotive design or airflow designs. It can also be used to control nuclear fusions for energy. But for all the scientific computings, there are also challenging scenarios, especially for we're into the high resolutions for weather forecast. Now we're kind of doing like 30 kilometer by 30 kilometer. For the best case, it's a 2 kilometer by 2 kilometers, which is already like 1,000 by 1,000 grade. If we go to 1 kilometer, will be 10,000 by 10,000 grades. If you're looking to the higher scale, it's going to be super large resolution that cannot fit into a GPU. Right. So for this high resolution, multi-scale features, we need to do corresponding parallelizable, decomposable models that can handle all this scale. A second kind of challenge is the nonlinearity and for the 3D complex geometries. For simple geometries, finite difference or spectral methods does pretty well. But for complex shapes, the meshing is a very tricky part. Usually people need to do iterative updates, make sure your mesh converge. And how to do the meshing for machine learning methods is also, I guess, core research questions. So we will going to investigate like embed geometry into latent space using geometric transform methods to have an efficient way to handling complex geometries. And in the end, I think generalization and the extrapolation is the key questions. If we train on the weather from the past 40 years, can we extrapolate to the new temperatures? Especially given global warming, there'll be new behavior and maybe new extreme events. Can we extrapolate to that? Or when we design car shapes, given existing shapes, can we find really new or novel shapes, even with different topologies? So this is the key research question we have in mind. So sometimes when we do machine learning for science, there are a little bit of over-optimisms. Sometimes machine learning people tend to claim early victories over twice-ish problems. For example, Jeffrey Hinton says that radiologists will be eliminated in 2016. But of course, radiologists are not eliminated. It might be kind of the case when you play chess, play Go, or train language models. You have infinite amount of data sets. Maybe you don't need experts to train the models. But for scientific computing problems, our data are very expensive to generate, and we need the experts, scientists to help us assess and interpret all this data. So I think it's very important to really work on the science part of the AI for science. But overall, AI is making real progress. For example, the chemistry Nobel Prize is awarded to AlphaFold. If we can predict weather really well, predict all the hurricanes up to 95%, I think we can also win a Nobel Prize for predicting hurricanes. Or if we can design an aircraft or design a rocket really well, I can also imagine winning a Nobel Prize to do this kind of design. So overall, there's a really bright future for AI for science. But the key is we need to handle the real world problems, not just academic small scale problems, but deliver the real cases and collaborate with experts, use mathematically well-defined methods. So it's my overall vision for these fields. Okay, we want to define mathematically rigorous methods. So we want to go back to the root of all the math. So when physicists and mathematicians define the problems, usually it's write down as partial differential equations. I guess everyone here are very familiar about that. In scientific computing, usually we just discretize the space and solve the equation, which could be very, very expensive. So the key research question is, if there is something shared across all the cases, maybe we can use machine learning data-driven methods to find the similarity and accelerate this process. So this is the idea of operator learning. That is to learn the solution operators of partial differential equations. So on the left, it is from the coefficient to the solution map. So on the right, it could be the temperature, how it evolved over the time, right? So on the left, it kind of corresponding to the carbon storage problem. We have different reservoir, a different sand and rock under the ground. What is corresponding pressure fields? So it's a coefficient geometry problem. On the right, it is initial value time-dependent problems. So given the temperature now, what is happening in next 6 hours? Most of the scientific computing problems can be formulated as an input-output map, which is a core of the targets of learning the map of solution operators. So compared to numerical solvers, where we usually somehow discretize the space and solve the system on the discretized space, here we're trying to discretize the input-output function space. And then given a new input, which come as a new functions or new image, we will try to find the corresponding output in the output function space. So we kind of turn solve optimization problems to a statistical inference problems. In this sense, it will be a lot faster because we don't need to resolve all the derivative to solve the equations. For example, if we need to resolve a domain, maybe we need a 1000 by 1000 grid. But to do the statistical inference, we just make sure the interpolation is fine enough. Usually it could be reduced to 100 by 100 or 50 by 50 grid. It's also true in the time steps. So maybe reduce from 1 in -4 to 1 in -2. It can jump across the time steps because it doesn't need to resolve time derivative in such a fine scale. So by doing a much coarser grid in both spatial and temporal grid, we can again speed up. In this way, we also find the similarity between all the input-output data set. And the key research question is, if we use machine learning model, how to define the most generic, scalable models. It need to be general enough not to handle just one specific cases, just like how attention compared to convolution methods. Also, it need to be parallelizable and scalable. When you have a lot of GPU, you need to solve large problems. For example, traditional methods such as convolution neural network or transformer, they're usually defined for machine learning tasks, such as image. We know the convolution neural network can identify edges and image pattern very well, but they may not be the most ideal efficient basis for smooth and continuous functions. Functions will have very high resolutions and differential structures. Maybe there are other bases that are general enough, especially using spectrum on a Fourier basis. So carrying this idea, we want to generalize the neural network from the machine learning vector to vector settings to the partial differential equations continuum settings. Just briefly recap, the neural network, the simple idea is just a combination of linear functions. For example, in the A times matrix A times the vector has a bias. So it's a matrix vector multiplications. And the nonlinearity is just a ReLU or JLU. It's a very simple nonlinearity. The idea is just when you combine simple linear functions and nonlinear functions to a deep network, it has the expressive power to approximate any continuous functions. So combine simple component to approximate complicated components. For differential equations, we kind of generalize this idea to integral operators, because for most differential equations, the inverse of differential operators is the integral operators. We can write out the solution U as an integration of kernel G, or Green's function G, with a force function F. When the G is a simple case, when it's easy boundaries, sometimes we can write out Green's functions in the analytical formula, but in general, we don't know that. So the key idea is to use the integral formulations or the fundamental solution formulations to solve differential equations. The idea is if we're using a linear system, the major computation is the inverted matrix. We can compute that in very high accuracy, but it is not very scalable. Inverted matrix is kind of an iterative process. It cannot be easily parallelized on GPU. But if we write things in the integral formula, it's very easy to parallelize. In a sense, it is just a sum across multiple transforms. So usually we think integral operators is much more scalable compared to like inverse matrix, which is the key of modern computing. Right. So to generalize from neural network to continuous neural operators, we just replace the matrix vector multiplications, the A times V, to a kernel transform, integral kernel transform. So now the input function will be transformed based on some kernel kappa to some output functions. So each block can be used to solve as a Green's function formulations for linear equations. And when you compose nonlinearity, it can be used to learn nonlinear, non-local solution operators. So the key idea is similar, by composing simple and global component together. It can be used to approximate any nonlinear, non-local, but continuous operators. Our earlier work is based on graph methods. Graphs are very flexible and they're commonly used to modeling meshes. So we can use a graph to approximate the integral kernels by taking a sum of the neighborhoods. We're also developing the multiple graph and interpret them as a multiple or multi-level graph methods that can do the integration in a more efficient way. But the most generic or the most flexible, easier to use methods we found is based on Fourier series. It's called the Fourier neural operators. We first restrict the integral operators to convolution operators, because indeed a lot of equations are translation invariant. So their fundamental solutions is indeed convolutions. And after we restrict the integration to convolutions, the convolution can be done by using full fast Fourier transform. So this is the famous convolution theorem, basically saying the spatial convolutions can be written as a multiplication in the spectrum Fourier space. So given the inputs, we just first do a fast Fourier transform, then multiply by a weight, which is theta is new kernel here, and then we do the inverse Fourier transform. It is very scalable. We only take n log n complexity in contrast to the plain n squared complexities. And it is very generic, especially for the smooth PDEs. So the implementation is very simple. The Fourier block consists of 3 steps. We first do a Fourier transform, getting the Fourier coefficients. We will usually truncate several Fourier modes to improve the regularity and as a denoise in steps. We'll apply the Fourier kernel R. We'll transform the basis, and then we'll do the inverse Fourier transform in the end. So there are 2 technical details here. One is we need to keep the spatial components here. if we don't have the spatial components, it's still going to be a local transform on the Fourier space, which will have a strong Gibbs phenomena on the discontinuity or on the boundaries. By keeping both spatial and Fourier components, we get the non-local in the spatial and the non-local on the Fourier space, which have a very efficient global non-local approximations. Another consideration is the weight. So there are two ways to parameterize the weight. One is I just set a preset thresholds, for example, 12 Fourier modes, and then I just learn a kernel for each of the Fourier modes. It is very simple, but it has a precise threshold. It's not very adaptive. Another way is I don't set a threshold, but I use a shared kernel across all the frequency. So in this sense, given whatever input, I will have the corresponding number of scale or frequency. And there's a shared kernel, like a MLP on the Fourier space, trickling all of them. So in this sense, it can be applied to as many as the Fourier series I want. This is called the adaptive Fourier neural operators. And these adaptive Fourier neural operators can also be interpreted as transformer architectures, where the fast Fourier transform is a spatial mixing. The Fourier transform is taking the place of the key and the Curry matrix, so key and value matrix there, and it learned its attention matrix based on the Fourier transform. In this sense, it kind of does the job of transformer, but with n log n complexity in terms of the number of tokens, and they can work on image. So far, do we have any questions about the Fourier neural operators and its derivatives?
If I can ask a question, if you want to move on to the next topic. So in a few slides back, when you were introducing the integral operator, you mentioned that the solution can be expressed using the Green's function. And so I was wondering, this slide, can we represent the solution of any PDE using this integral operator, or only just elliptic PDEs can be represented like this?
Only linear PDEs can be represented in this way, right? So because the inverse of a linear PDE is a linear integral operators. But the key is that even each component learn a linear transform, when we compose it with nonlinearity and have a deep operators, it can be used to approximate nonlinear solution operator for nonlinear PDEs.
Okay. And have you applied this to nonlinear PDEs as well?
Yes, so we're mostly working on fluid, mostly Navier-Stokes equations, which is a nonlinear PDEs.
Right. Okay, fantastic. Okay, thank you. Hassan?
Yes. So can you also explain what if you want to do a Fourier transform on non-uniform like graphs, how would you do that efficiently?
That's a good point. So for non-uniform Fourier transform, there are usually two ways to do that. One is we first do some local convolution or local transform to interpolate to a uniform space. Another class is we directly do the Fourier transform as integrations. So the function is taking an inner product of the Fourier coefficients. But I guess it can also be interpreted as doing a Fourier interpolations into the space. But I guess in the third sections, we're going to the geometry parts. So all the inputs are non-uniform grids. We're going to talk more on how we tackle them.
Thank you.
Alex?
Hi, thanks. Just a quick question. It wasn't clear to me when you were talking about the Fourier layer and you were discussing the Gibbs phenomenon. If does the number of layers affect the the number of frequencies in the frequency domain that can be considered when filtering the operator, because we're talking about, like, if we have sharp edges, very high frequency changes in our function space, do we need a deeper network to accommodate that, to have more weights and more terms, to have more frequencies, or is there a relationship there at all? I didn't quite understand.
Right. So we have two ways to control the frequency. One is the number of layer, as you said. Another is truncation of the Fourier basis. If we truncate to only the low frequency, then we will of course discard most of the high frequency, right? But for the general cases where we don't truncate, but just using a shared network, it will preserve all the frequency. It depends on smoothness conditions we have. So for like nonlinear small detail problems, usually it's good to not truncate.
Got it. Thank you.
Thank you. Okay, so I guess maybe I should move on. So after we have been developing the Fourier neural operators, we have some theoretical work to show it can be used to approximate any continuous operators. And for specific problems, we can also get a bound on the number of parameters and commutation flows to get the solutions. For this kind of theory is usually based on linear approximations, or we mimic existing solver, such as the Fourier or pseudo-spectrum solver. But overall, the approximation theorem, we have to somehow adapt the methods to use the existing results from the numerical solvers. We haven't really get a new result that's based on nonlinear approximation of nonlinear operators. So just a little bit of the sketch of proof here. So given a target operator phi, we will just do a linear expansion. Assume the space is compact, this expansion will converge. And then we just use a neural network in each channel to approximate each functional basis of these expansions. So if we can discretize and to approximate the input-output function space, then everything is finite. We can just use the existing neural network to approximate this finite to finite space. But I guess this theorem is still not showing the real advantage of the nonlinear approximations because it's still a linear expansion of the operators. Okay, so results. In the beginning, we're mostly focused on 2D PDEs, such as Navier-Stokes equations with relatively low Reynolds numbers, two examples. But after that, we have been collaborating with a lot of experts in each domains to deliver real cases. We have been talking about the weather forecast and the carbon storage with multi-phase flow. So next, I'm going to talk about the aerodynamic SFD and the fusion reactors. So for the fusion, we're collaborating with the UK Atomic Authority Group. So they have a very, so thanks for NVIDIA, we have a cool visualizations. So this is tokamak machines that have plasma in the magnetic field inside that. And we can use the Fourier neural operators to approximate the plasma fields. So usually we have one operators to compute the equilibrium with time average states, and we can have another operator to approximate the time-dependent acceleration states. If you can control this in a very fast time, it can be used to do prediction and then feedback control to give you a, so that it doesn't get too hot and blow off. We have been working on many applications across many university and companies. Overall, we find if you have a big data and big model, it is the best use case for AI-aided scientific computing. If your data is not enough, we just cannot learn very good models. It will overfeed and not generalize. If the problem is too small or the model is too small, usually the existing solver they has been solving this problem, killing this problem very well. So very interesting in hard problems where we can get a sufficient amount of data. But we know that data are expensive. What we don't have really a lot of data in the limited data regime. The overall idea is we can do some self-supervised scheme to augment the learnings where we borrow information from physics or other physical properties. The two ideas here, one is use physics-informed learnings. So the idea is simple that maybe we can, beyond the data loss, we can also use the equation loss here to learn operators. So compared to just using pins, we're also learning operators across multiple instances. So it's easy to share information across across equations. One technical consideration is how to take derivative exactly. But the good point is, since we use Fourier series to express the Fourier neural operators, all the Fourier series can be exactly differentiate. We know that derivative of sine is just cosine. Derivative of cosine is just minus sines, right? So we just write out all the exact derivative on the Fourier space and use chain rule to compose it with the nonlinearity and all the projection layers. So by doing that, we'll get the exact derivatives in efficient manners. And we're not just evaluating each point at a time, but we're evaluating the analytic series of all the points on the space by taking Fourier derivatives. So there's examples where we're doing Navier-Stokes equations with a ring number 500. It can solve it to a decent accuracy. It kind of works like a spectral method. We find the optimization is more scalable compared to, say, basic PIM methods because we're optimizing the Fourier series on the function basis. So it converts a lot bit faster. But for this 2D periodic cases, the sealed spectrum solver is killing it. I think the solver is just too good for the 2D periodic simple case. Overall, it is still a little bit tricky to compute the derivatives. We need a relatively fine grid to have a fine enough computation to evaluate the derivative. Just a little bit here. So recent new direction is to use the stochastic formulations. So given Poisson equations, you can write out the corresponding stochastic form. It's kind of like using a particle-based solvers versus Euler and grid solvers. So in this sense, we don't need to compute the derivatives, but we just evaluate the sum. Then there's a solver based on Monte Carlo methods or Cancer-Fear. But I'm going to skip it now. A second class of unsupervised, self-supervised learning is to use consistency between different scales. We know that PDEs are dimensionless and they're self-similar in some sense, and we can change the variables and enforce the relationship, self-similar relationship between different scales. For the example of Navier-Stokes equations, so the scale is really described by the viscosity numbers or the domain size, both of them describing the Reynolds number of the problems, right? So for simple, smaller scale problems, usually the grid is very low resolutions, that's sufficient. For higher Reynolds number, usually we need a higher resolution grid. And it's expensive to compute the data set on a higher Reynolds numbers. So the question is, can we train on lower resolution the Reynolds number datasets to generalize and extrapolate to higher cases? So the idea is to rescale the parameters and domain size. Basically, we can do a change of variables, say we define y equals 2x. So it will kind of just zoom in these figures to a larger domains. But so far, it just has the same range number. When you zoom in the large domain, it gets smaller viscosity. And then we'll restrict to a subdomain, which will essentially define a subdomain or smaller subcases. So in this sense, we have a global models or global problems and the local model and local problems. And we wish to use a universal foundation models to capture both global and the local evaluation and make sure they get the same solutions on the outputs. So what we call the consistency loss. So on the top, it is global problems. If we have data sets, we can restrict to subdomains of both input and output to get the local problem. And we evaluate the neural operators on both global and local cases, which will give us a consistency loss. It's a mismatch between the two cases. And this can work without data. So if we don't have label data U and just randomly initialize some coefficient A, we can first use a model to give some rough prediction of U, and then give the model to roughly prediction of the local U and enforce the matching of them, consistency of them. We don't even need to have a solution U to enforce such consistency. So it's a way to augment the data. We don't have enough data to do the supervised learning. So to simple theorem, the first lemma is it is indeed consistent. So the global cases and local cases should be the same. It's based on the uniqueness of the PDEs. So if they had followed, satisfy the same solutions, satisfy the same boundary, then it needs to be the same as PDEs, right? And another theorem is that basically domain decompensations. If we train the operators that satisfy the scale consistency pretty well, then just like domain decompensation, it works on each subdomains and it will give you the true solutions, right? So by training the self-consistency loss, you can indeed find out the solution operators. We show some examples where we train on many different scales. So not just one global and one local scales, but we have written a number from 200 to 10,000. So given one training cases, in this case, the green bar is the baseline methods. It has higher error, generalized to lower and higher scale. The orange is our scale consistency methods. It reduce error across the lower and the higher scale. So it actually generalize better to unseen scales. It can also have been used for the real cases. For example, given the weather forecast, it will be very hard to fit a high resolution in the global scale. So we can first use a relatively coarse model on the global weather, and then use the local models on high resolution local models to zoom in to the local scale. So there's a figure of the NVIDIA core depth. They do 2 kilometer resolution of Taiwan. Similarly, we can use one foundation model to both do the global prediction and the local predictions. Okay, so any questions for these sections?
In this example, are those like the global and the local forecast correlated at all? Because they seem very different.
Right, so for this example, the global prediction is a input to the fine-tuned local predictions. For here, they're using two separate models. So the local models are used to correct and augment the global predictions. So it has more smaller details.
So is this a failure case then?
Sorry, so let me make it clear that the global model is kind of failed to give you the engaged details, but the local model can give you much finer details. That's what we want.
I'll pass it to the next guy.
Yeah, thank you.
Yeah, I can go next. I know that in a lot of this, you are motivated by spectral methods. And those methods are really good with periodic boundary conditions. And in a lot of cases you showed, you're also using periodic boundary conditions, but in reality, we don't always have periodicity. So can you comment on that, or if you have done anything special to satisfy the boundary condition? That's one question. Another question I have is in general about, I've read your papers, and you talk a lot about being mesh agnostic. And so I was wondering if you also could comment on that, because your previous response, you mentioned there's an interpolation for Fourier methods, for Fourier operations, and I don't understand, where the mesh independence, would be there. So yeah, two questions. One boundary condition, one on the mesh agnostic. Thank you.
Thank you for the questions. So for the periodic boundary conditions, most of the cases we're working are not periodic boundary conditions, especially for this case, when we restrict to a subdomain, it is obviously not periodic. But it is still okay to use Fourier series. One case is because we're usually extended to a larger domains using paddings. So it works kind of like Fourier continuations. We just need to match the targets on the original domain, and it will have some whatever continuation on the larger domains, but it's still fine. So in some sense, it is like a wavelet, but we only use the critical parts on the target domains. And there's a larger domain of margins. We don't really care. For the second questions, so it's about the resolutions, dimensions. I think there's a good example when we learn a foundation model of multi-scale. It need to be resolution invariants to tackle the global and the local instance, especially there at different resolutions. So I have a 500 by 100 global resolutions. Truncate that, it will be 100 by hundreds. So my model should have the similar parameterization to across with high resolution and low resolution inputs. And largely speaking, when we have a training foundation model across multiple data sets, there's also encounter a lot when we have a different resolution of data sets. It might be okay to prepare a unified data, but that will be the same resolutions. You probably have only truncate to say 128 and this 128 frequency. You cannot learn beyond that. Yeah, sorry, I'm a little bit short of time, so
I appreciate that.
To just go to next sections. Yeah, I think it's the most related part for Autodesk, where we're trying to design shapes with non-uniform mesh. So I think we all know that 3D computational fluid dynamic are very expensive. So on the left, it is a simple safety car simulations. It's a very rough, non-convergent simulation, still take 1 hours. On the right, it is by NVIDIA, where we use a GPU-based open form simulations to do runs time every simulation. To make sure it converge, it can take 10 hours, and just with a simple Harman body kind of shapes. And the goal is that maybe we can learn operators given the input shape and mesh to directly predict the pressure fields and velocity fields of this design. So one like a straightforward idea is we can embed it, the input mesh into a uniform latent space where we can do efficient computation in that. It's kind of similar to the immerse boundary case. We just put a uniform mesh in the latent space. So given the input mesh, we just connected with all the points using a graph method or graph neural operators that kind of do an interpolation or learned interpolations to go from the uniform mesh to the latent mesh. And in the middle, we do a Fourier neural operators, that is a very fast and scalable operators on the local mesh. In the end, we again do a neural operators to interpolate back to the space. So in some sense, it is similar to a non-uniform fast Fourier transform. We have some local operation, local interpretation in the end and in the beginning, and the middle way to Fourier methods. And this method is fine, it's flexible by doing this graph methods in the end and the beginning. It's also fast by the fast Fourier transform. It delivers some, I think, it's great results. The pressure fields relative error is about 5%. Also thanks to my colleague at the media, they help us generate the data set. But again, it's kind of expensive because we need to use a fine 3D latent mesh. Usually need to be like 100 cube, which is 1 million mesh points, like kind of same the size of the mesh size. So it could be kind of expensive, and the accuracy or the geometry really depend on the resolution of the latent mesh. If the mesh is too coarse, we just miss out the small detail, right? So another related idea is to use deformation or geometry transform to learn an adaptive mesh. So adaptive mesh, there are two kind of methods. One is adaptive refinement, like when using a finite element methods, you can add more points. Another class of methods is to using a fixed meshes and the deformed mesh. It's called adaptive moving mesh. So in this case, we will still have a uniform mesh where we can do fast Fourier transform, but we're going to learn a deformation or a coordinate change, coordinate map that will align the shape into the input physics. For example, if I have a car, we'll try to align all the most of the density of mesh along the surface of the car, right? So it has a good mathematical implementations. For example, it can be used to do Chebyshev transform. Chebyshev transform is basically using a fast Fourier transform on latent space with a cosine grid, right? So by doing that, you will kind of rediscover Chebyshev transform if we restrict this coordinate transform to a cosine transform. In general, we can use any transform. It can be used as a cylindrical transform. We just need to have a uniform latent space. If it's a torus, then it's fast Fourier transform. If it's a sphere, then it will become spherical transform. I guess the key question is how to find such a transform. Because given a different mesh, this transform cannot be analytically read out. So one direction is we just learn this transformation neural network, right? So in this sense, we are going to learn a small components this neural network as a transform, and then offering operators on the latent space. It seems to work well for the 2D airfolio examples, but it's still 12-ish examples. It has better convergence compared to the solver based on Julius. But still, this transform, it doesn't necessarily guarantee to be a continuous transform. Another interesting idea is to use optimal transform as a geometry transform. Optimal transform, for example, here, if I deform density function, uniform density on the sphere to the given density of the mesh, because I view the input-output mesh as a density functions, it's quite natural to do that with optimal transform. And most importantly, it can be done in a fast manner, where the exact for optimal transform is a cubic time. We can use sinkhorn with a quadratic time, or for this 3D cases, there are fast approximation that can be done in the linear time. So I think it's a generative method that give you any mesh and project it to a uniform latent space. Right, so this optimal transform, we can use a transform map, which is one-to-one map. It can use a transport plan where I can split the mesh point into multiple mesh points. When we split that, it's kind of like a graph connections. So compared to a standard graph based on nearest neighbor search or ball connection search, this optimal transform map will preserve the global density, so preserve the global structures. So we can work on the driver net car-ish datasets. It get a better accuracy compared to the latent space-based methods. Most importantly, it's really fast. We only need to do 2D Fourier neural operators compared to the 3D neural operators. So for 2D, we only capture on the sphere. So it's 1 dimension faster compared to 3D transform. Okay, so in the end, overall is my last year of my PhDs. I've been delivered some of the work I'm really happy about. Also, I'm honored to cooperate with a lot of experts and colleagues to have applications in weather forecast, also in fluid mechanics, solid mechanics. Yeah, so for the future work, I think it's very promising to deliver a foundational-ish model that should be able to generalize across different initial conditions, boundary conditions, and coefficients. Further, it should be handle like larger scale and smaller scale. For example, I can train a coarse models on the overall scale and the local model to zoom in the mirror or the tire, the smaller complex geometries. And ideally, it should handle the shapes, which is the tricky-ish part of the scientific computing. And beyond that, we maybe can borrow a data set from multiple family of PDEs. For example, can train with weather and other fluids. They may have the similar physics. We can also pre-train with maybe graphic or image or even large language model. That's also possible. Just in the very end, we also been working on libraries. So for Caltech, we have this neural operator library. It contains all kind of models, FNO, adaptive FNO, or geometry-based FNO, all here. At NVIDIA Modulus, it is computer-aided design teams. They also have neural operators, but they also have a lot of cool applications. This car and the weather, it's a real cases. They're all open source. It's cool to check out. Yeah, so that's the end of my talk. I also thank all my colleagues from Caltech, from other university and teams, and my undergrad mentees. That's a reference. Okay, thank you for the attention.
Great, thank you very much. I really appreciate it. There was a lot of material to digest for sure. Any questions for the last part from the audience?
Yeah, I'm just I noticed like your geometry is generally watertight, or you can do a projection from a sphere onto the mesh. What happens if you want to support flow inside as well as outside of the geometry? Cases like
Yes. So most of the machine learning methods are generic enough. It doesn't require the watertight mesh. For the latent space methods, it indeed do a 3D spatial volume computations. So it can compute what inside and outside. It doesn't need to be watertight. For geometry transform, if we want the transform to be a diffeomorphism, then it probably need to be watertight. But if we use optimal transform methods, it will give you a discontinuous transport for non-order type methods. But it's still fine. It will give you some transform, even it's not watertight.
I can ask a follow-up question. What if when you wanna, so for the new geometry that you're creating, it is topologically different than your reference geometry, for example. There, like you want to add a hole. How do you handle these cases?
Yes, I think that's a really hard case. So most deformation-based methods kind of assume a uniform topology. So if you have a hole, I think this method will probably not work for that. I guess I will need a new type of a parameterization for whole.
Right.
Mhm.
Any other questions?
I've got one. Thanks a lot for the great presentation. For injecting the PDE, do you also have one method? Do you only have one method, which is through the loss function, which you call physics informed, or do you have in your publications other methods for just imposing or injecting some sort of PDE knowledge?
I see. So for physics informed, here we just consider the equation here. I guess some of my colleagues, they're trying to inject some constraint, for example, energy constraint or a divergent-free constraint. But I guess they can depend on like exact derivatives. If we use Fourier derivative, it's still tricky to do that for non-periodic boundary. For data-driven cases, non-periodic boundary are fine, but for physics informed, it causes kind of stability issues when you compute the derivative, right?
So can I ask a follow-up quickly? So if you can learn an operator, let's say you can learn Laplacian, you can learn divergence. Is there any way to add a few of these operators together to construct, let's say, the PDE that you want, and essentially expect it to work? Or have you done that?
Oh, I haven't done that, but I think it's a really cool idea. For example, for Navier-Stokes, if you learn diffusion, learn advection, can they compose them? So there are some foundation models that try to do that, but I think they haven't really do that for Navier-Stokes. They do advection, diffusions. So if I have a advection term and diffusion term, it can kind of mix them.
All
But
right, sounds
yeah,
like something we could collaborate on.
yeah.
I'm just checking with the time. Zhangli, thank you so much for making time to give us this amazing talk. I'm glad a lot of researchers from Autodesk were able to join and listen in. And yeah, thank you everyone for joining. We have another Research Connection series this Thursday, so feel free to tune in on Thursday as well. Thank you, Zhangli.
Thank you.
Thank you very much. I appreciate it.